Assalamualaikum and a very good day. I bid to my panels. My name is Muhammad Hafiz bin Razi. Will present my final year project, which is the study of structural flexibility of badminton shuttlecock. My supervisor is Dr. Zainul Helmi bin Solihin. Next, I will talk about my introduction. Badminton is one of the famous sports in the world, especially in Asia. Shuttlecocks are usually made of natural feather or synthetic rubber, which is very light. The average mass of the shuttlecock is around 5.3 gram. It also is made of 16 feathers of goose with a skirt diameter which is around 65 mm. The materials plays a very vital role to influence the flexibility of the shuttlecock. In this project, shuttlecock is a very important equipment that used in the game of the badminton with the presence of aerodynamic characteristics. The studies are focusing on the behavior of the aerodynamic for the shuttlecock and the analysis of the flexibility of the shuttlecock. Aerodynamic behavior can be determined because of the wind applied towards the feather. There are two softwares that will be used, which are CATIA and ANSYS softwares. By using ANSYS, which is CFD, computational fluid dynamics software, is to analyze the structure interaction of the feather, while the CATIA is for the design of the feather. Next, the objective, scope and limitation. The objective is to investigate the behavior of the aerodynamic for the shuttlecock, to analyze the flexibility of the shuttlecock, and the scope of the study is focusing on the design and analysis of the feather. The design of the feather will be modeled through CATIA software, and the analysis of the feather will be done through ANSYS. The value of the wind speed, flow and force towards the feather. The dimension of the feather will be the same due to original size of the shuttlecock are the limitation of the project. Next is the methodology. From the start, we can see we will start with the CAD modeling, Cad modeling, with which we use CATIA software to design the feather, and we will go through the structural analysis through CATIA to make the analysis, and then we will get the result. For the mathematical modeling, the structural analysis was collected from the calculation that have been done on the feather. It involved the Navier-Stokes Equation, Bernoulli Equation, deflection equation, and others on the feather. From this equation, we can see from the governing equation, we assume that steady flow, incompressible, open channel, no heat or work transfer, and others to make the equation. After the continuity was satisfied by the given velocity, when the continuity was not satisfied, the analysis can't be progressed. So next, the Navier-Stokes equation was considered on the x direction, which is, we can see x direction of Navier-Stokes. After we solve with the boundary condition, then we will go through the Bernoulli equation, which is pressure plus kinetic energy plus rho GH equal to stress, and stress for all the used equation, the SI unit was in Pascal, so all the pressure must in the same unit to calculate the equation. From the stress, we can get force over area, and the strain was about to measure how the product was stretched or deformed. Strain occurs when the force was applied to an object, and the formula is the change in length divided by the original length. For the CAD modeling, computer-aided design, was to design the feather of the shuttlecock. CATIA V5 is one of the best software to design and modeling of the product. First step of the modeling was by collecting the data of the feather measurement. It was easy to use to design by following the original measurement of the feather shuttlecock. And from the design, we just used the original size, and the feather was around 0.0065 meter and the width was 0.0026 meter. Next, in the ANSYS software, we will take the fluid flow fluent, and the first part we have to do is the geometry. Geometry part is the fluid flow part, and we have to do an enclosure must be done. The feather that import from CATIA was located inside the enclosure with measurement 650 mm for the x-axis and 100 mm for the y and z-axis. The measurement of the enclosure must be 8 or 10 times bigger than the feather. Next, we will talk about the meshing. In this part, meshing is one of the most important process by performing simulation by using FEA, finite element analysis. A mesh usually was made up of elements which have nodes. Nodes, which was the coordinate location in space that can vary by element type, was present of the geometry shape. In this part, different values of nodes were collected to plot a graph to make comparison between all the nodes. By simulating different type of relevant center which were coarse, medium and fine, the data was combined with different type of quality smoothing that have low, medium and high to acquire 9 types of nodes. From this table, we can see we have 9 different of nodes, which are 5,000 to 14,000 nodes with different relevant center and smoothing. So we can see different nodes have different velocity impact on the feather. The higher the nodes, the higher the velocity will impact through the feather. As we can see from the graph, we will choose 14,292 nodes because around 11 to 14,000 is the most constant nodes for the velocity that impact on the feather. So we will choose these nodes. Next, I will talk about my result and discussion. My result is we can get the equivalent stress or von Mises stress. The result will focus on the total deformation and equivalent stress of the feather with different speed of velocity, which were 25 meter per second, 50 meter per second until 125 meter per second. Each simulation I add 25 meter per second. As we can see from the table, 25 to 125 meter per second velocity of wind, we get the different value of minimum equivalent stress and maximum equivalent stress. For the most highest maximum equivalent stress is on velocity 125 meter per second. As we can see here, the higher the value of velocity, the higher the velocity of wind, the higher the maximum of equivalent stress of the feather, which is from here 15,406 Pascal. Next, this is the graph for the velocity versus maximum equivalent stress. For the x-axis is the velocity and the y-axis is the maximum equivalent stress. And you can see it is increasing. When the velocity is increasing, the equivalent stress for the feather also increase. Next, this is the picture of the equivalent stress for 25 to 125 meter per second. They are different. They have different value of maximum equivalent stress. So next, the results is to find the total deformation of feather with same value of velocity, which are 25, 50, 75, 100 and 125 meter per second, and the total deformation of each of the velocity of wind. As we can see here, the higher the value of velocity of wind, the higher the deformation of the feather. Same as the result, we can see it is increasing when the velocity of the wind increase, the total deformation on the feather also will increase. So this is the picture that I screenshot from the NC software. From the software, we can see the feather is deflect or deform with the different velocity of wind. To get the different we have to find the deformation of the feather, and this is the turbulence of the velocity of the feather. So I think that's all from me. Thank you.